Yes.
So I'm Toryn, and I'm presenting this work on formal languages for reward function specification and reinforcement learning, which my co-author is shown here, and I recently published at HCI 2019. So to give some background in reinforcement learning, the agent interacts with an environment by performing actions. In response to an action, the agent ends up in a new environment state as determined by the transition probabilities and gets a reward according to the reward function. The agent typically starts not knowing what the dynamics of the environment are, so has to explore to find out how to maximize reward. Here's an example, a simple grid world that we call the office world. The agent is the purple triangle, and there are walls in various locations like the coffee machine and the mailroom. Various tasks can be defined in this environment. Let's consider the task of patrolling locations A, B, C, and D in a cycle. For reinforcement learning, we have to specify the task in terms of a reward function, which might be derived from a formula in some formal language like linear temporal logic, or just programmed directly. So let's suppose we have some code. It gives the agent a reward of 1 each time it completes a cycle. Now, the reward function is typically treated as a black box. And to show what I mean by that, suppose that the agent moves up one space. Now, it queries the reward function about what reward it should get from ending up in that space. And the reward function responds by returning the reward, in this case 0, since the agent hasn't completed any cycles yet. The agent does not make any use of the internal structure of the function. In previous work, though, we proposed exposing the structure of the reward function to the agent so as to allow it to learn faster. In particular, we proposed representing the reward function with a structure called the reward machine in a paper in ICML 2018. So suppose that we have a symbolic vocabulary to describe the environment. For example, each of these propositional symbols might be true in the office world if the agent is at a correspondingly marked location in the grid. Then a reward machine has a set of states with an initial state and also a set of transitions, each labeled with a logical condition using vocabulary and a reward. Technically, a reward machine is a type of mealy machine for those of you who are familiar with that. As the agent acts in the environment, it passes the labels of the environment states it visits to the reward machine. These inputs cause transitions in the reward machine, and it outputs rewards to the agent. Importantly, the reward machine doesn't have to be treated as a black box. The agent can make use of information about which reward machine state it's currently in and the structure of the machine. We've developed algorithms that can make use of this information that reward machines expose to learn faster. And these graphs are algorithms in black and red outperform the baselines. Finally, if you want to specify objectives using formulas in temporal logic or other formal languages, it's well known that regular languages can be converted into DFAs, deterministic finite automata. We show that from there, they can be converted into reward machines, after which you can apply algorithms developed for reward machines. So reward machines can be thought of as a sort of useful normal form for representing reward functions. There's code for reward machine algorithms online, and also recently an online tool for translating formal languages into reward machines. And that's everything. Thank you.